Okay, so now today's lecture is really just an extra lecture. It's cultural lecture for you. You may be asked some questions about it in the exam. Won't be very difficult questions because you won't have done an exercise on this stuff. But it's an interesting topic. It's closest to do with device physics, which lies at the root of this neuromorphic engineering stuff. And it's related to memory technology and new kinds of devices for memory technology that might apply to neuromorphic systems of one type or another a little bit. But it has to do with the shrinking of the MOSFET and overcoming short channel effects and using silicon on insulator technology and moving to FinFET and to nanosheet field effect transistors. So that's the first part, is about shrinking of the MOS transistor. And then the second part is about new non-volatile memory technology, going past dynamic random access memory and static random access memory. Here's the silicon process technology international technology roadmap for semiconductors from 2019, or I guess it was actually from about 2015, because it actually predicted shrinking down to 5 nanometer technology now. If you look at it, it's actually an exponential shrinking of feature size, where it's basically, according to everybody who's in the business, they say it's now stopped. You know, technology won't shrink anymore. What will happen is it'll get more and more integrated into 3D and things like that. And, you know, people are going to continue to work on architectures, like the organizing principles of digital systems, to make them more efficient. Gordon Moore was one of the original Fairchild 8 who founded Fairchild together with Bob Noyce and Gene Horney and the other people that basically left from working with Bill Shockley. Bill Shockley was a physicist. He was a bit of a megalomaniac and a crazy guy. He pulled together the top semiconductor people at the dawn of Silicon Valley to start Fairchild Semiconductor. Basically, the other 8 recognized that Shockley was basically a bit crazy, and they left and they started their own company, Intel. And Gordon Moore was deeply involved in that. Anyway, it was Carver Mead actually who coined the name Moore's Law for an observation that Gordon Moore had made about the scaling of the number of transistors with time on a chip. And this is historical data, but I think it's basically flattened out now. But anyway, it's been led by the shrinking of transistor sizes. So you guys have been learning all about surface channel MOSFET transistor technology and bulk silicon. Bulk silicon means that you have a wafer and you implant the sources and drain in a substrate like this. On the surface, then you grow some silicon dioxide. You then put gate on top of it and use it, and then you pattern the gate material to get rid of the gate where you don't want it, and then you implant the source and drain self-aligned by the gate. So the gate blocks the implant to the source and drain, and then you form a transistor like this. And this is still the mainstay of silicon technology. But now when you buy, you know, that's all the physics you guys have been learning now, and it's still like the way most chips are built this way, especially mixed signal chips that do analog and digital stuff. But you've probably all heard of that you have undesirable effects in short transistors. We told you a little bit about those, like carrier velocity saturation and drain-induced barrier lowering and punch through. You guys might remember that we talked a little bit about that stuff. And so these are the things that really get worse and worse as you make the channel shorter and shorter, because the source and drain regions, the depletion region around the source and drain gets closer and closer, and as a function of voltage, they can actually touch each other. And when the source and drain depletion regions touch each other, then the threshold voltage changes. You get this drain-induced barrier lowering. Because of the extremely high electric fields in there, you get carriers accelerated to very high velocity. This damages the gate oxide. There's all kind of weird effects that happen when you really make the transistors super short. And why do you want to make the transistors really short? Because the shorter the transistor, the more current you get for the same voltage. And the more current you get, the faster the digital circuit is. So basically, the shorter the transistor, the quicker the electrons can get across. So that's why making the channel shorter and shorter is so important, especially for digital, where you want to minimize gate delay. And if you can minimize gate delay, you can get up the clock frequency You get at the clock frequency, you get more compute per unit silicon area. So your silicon area efficiency goes up. People have made all kinds of process improvements to control the short channel effect, like using thinner and thinner gate oxide. But of course, if you make the gate oxide too thin, then you start tunneling through the gate oxide and it becomes more and more delicate. So you have to lower the supply voltage, which is good. But it also lowering the supply voltage means that you have less voltage to drive the electrons from source to drain, or the holes from source to drain. So that slows you down. So you have these trade-offs, complex trade-offs. People have done all kinds of weird things like straining the silicon technology. They actually introduce a strain along the transistors that's induced by the manufacturer of the transistors that increases the mobility of going along the transistor channel. And over the last, I guess, 5 or 6 years, maybe decade or so, they've went from using a silicon dioxide gate to so-called high K dielectric material like hafnium dioxide. It was actually introduced by Intel in a 45 nanometer process. Now it's widely used in anything below 45 nanometer. And this particular insulator, and boy, it was so expensive to get it online. It must have cost several $1 billion to bring this new gate oxide onto the line, this high K dielectric. But you get much higher dielectric constant. What is that good? Because then for the same gate oxide thickness, you get a much higher capacitance, much better control of the channel. Okay, but anyway, people went about as far as possible with this high K stuff. And then they said, there's a big problem, the bulk. The bulk is a big problem because the bulk is always controlling the surface potential here somehow, this voltage. By kappa, the bulk is controlling things. So what if we could actually do something like silicon on insulator? Instead of making a source and drain over P-type bulk, let's make a source and drain and just build it over an insulator. And so now your transistor is literally a piece of silicon, which is lightly doped, surrounded by source and drain, which are heavily doped on top of oxide. That's silicon on oxide technology. And do you know one place that's widely used besides high-speed circuits? What's the other place do you think it might be used? Is silicon on insulator. It's used in Swiss technology, in fact. Anybody have an idea? So what's one source of power here, right? The transistor leakage from VDD to ground through the transistors along the channel, right? Another source of leakage is from the source to the substrate. So you have this reverse bias junction, N to P junction. So you actually lose power just because the junctions have a dark current and they leak. But does the SOI have that? No, it doesn't have that because there's no bulk to leak to. So one place that SOI technology is used a lot is in ultra low power watch circuits. So they actually build these watch chips on SOI to reduce the junction leakage to get the battery power consumption even down another factor of 10. Down to, I heard that a Casio watch burns about a tenth of a microwatt, about 100 nanowatts. The whole watch chip with all the complex stuff on it by using SOI technology. Okay, so that's one way you can get rid of some of these short channel effects and bulk effects. Now, how many people, I guess almost everybody here probably heard of FinFET technology. FinFET just stands for the name that it's like a fin sticking out of the silicon. This was proposed in 1999 and it came online maybe, again, about a decade ago, maybe 5 years ago in mass production. And the way it works is a bulk silicon technology. But the main thing about the transistors is that they are formed by these fins of silicon that stick out of the substrate. Don't ask me how they fabricate this stuff. And now the gate is, again, polysilicon. It's separated by the insulator here. And the source and drain are at the two ends like this. So now the gate surrounds the source and drain connections, right? So now the current flows from source to drain, but it's surrounded by this gate. And so the FinFET transistor is defined by the channel width. You can't make the channel too wide here because if you make the fin too wide, the gate doesn't have control of it anymore. It only has good control if the fin really surrounds the silicon that's conducting the current. And you have a fin height, and the fin height is set by the maximum height of fin that you can etch things and grow them nicely. And FinFET technology is used widely in production now. For example, Samsung application processors, MediaTek, Samsung's latest Exynos is built on like an 8 nanometer FinFET technology. It's widely used for logic chips all around the world. But there's a problem with this FinFET. Do you know what it is? So any one transistor has limited width because you can't make it too wide, right? So any one transistor has limited strength. And because the aspect ratio is not really controllable. So you can kind of make the transistors longer by making the gate wider and wider, but you can't really control the width. And so you can't really scale it to 3 dimensions. So that's why over the last couple of years, people proposed the latest wrinkle on this. This is actually really cool. Well, people use multi-FinFET, but that's just transistors in parallel. In fact, when you do analog design in a FinFET technology, all you do is take multiples of transistors. You can't actually change the geometry of the transistors. Everything is like an integer ratio. And so, so 16 nanometer FinFET came in 2014, and now people are in production on like 7 nanometer, even 5 nanometer I've heard. Okay, so here is the latest thing that is in this lovely article in called grandly titled "The Last Silicon Transistor in IEEE Spectrum" just a few months ago. It's called a stacked nanosheet FET, and it's targeted for 3 nanometer process technology. 3 nanometer is like the feature size of the UV fab. And so the idea is in a planar FET, like you just saw, you have the structure we just saw, right? With source and drain and gate crossing it. And in a FinFET, you have the source as a kind of a fin and the drain as a fin. And then the gate kind of surrounds this fin. But in a stacked nanosheet FET, the gate completely surrounds the channel regions, and there are multiple channels of silicon where the current can pass from one side to the other. So if you've been in San Francisco and been on the Bay Bridge, you have like a bridge with multiple levels that crosses the bay. There's just like the nanosheet is multiple channels stacked on top of each other. Let me show you a little bit more detail of that. So here's an actual cross section. But in this stacked nanosheet FET, the gate completely surrounds the channel regions to give even better control than a FinFET. So let's see if we can understand this. So these gray regions here are the multi-channels of silicon. This dark gray region, I guess, is the gate oxide, is the gate itself. And probably this white region is some isolation between the different transistors of the multi-channel FET. And the really cool thing about this multi-channel FET is that your gate width is not restricted anymore. You can make your transistors wide, and the gate still has control of them because the gate goes all the way around them. Now you might ask, how is it possible to fabricate something like this? And so the steps, at least as reported in IEEE Spectrum, is like this. You make a superlattice of silicon and silicon germanium that's grown on top of a silicon substrate. So here's the silicon and here is silicon germanium. And then there happens to be a chemical etch that etches away the silicon germanium and just leaves the silicon behind. Okay, so it's kind of like silicon surrounded by air or vacuum, most likely. And then you can use atomic layer deposition to build a thin layer of dielectric on the silicon channels, including the underside. When you do atomic layer deposition, you kind of surround this stuff in this atomic vapor, this plasma, and then the atoms stick to the silicon. It doesn't matter whether it's on the top or the bottom. It's like a gas that'll just stick on all sides. So you get dielectric all around it. And then on top of that, you build a metal gate to connect to that gate dielectric. It's really magical, isn't it? And so this promises to be the next generation silicon technology. I guess you would regard this as some kind of silicon on insulator, right? Because there's no bulk silicon anymore. You just have these multiple channels hanging kind of surrounded by metal gates that are separated by some magic gate dielectric. So that may actually be the last silicon transistor technology. So do you have any questions about this stuff? Has anybody worked on that, or is there any other courses that you've taken that are about this kind of stuff?
I feel like I kind of missed something, but how are the channels which are higher and like detached from the base affected by what the advance of the base in this case?
Didn't really understand the question. How do you connect to these at the end, you mean?
No, can I like at the base when we have the two black things, we have like, I guess the source and the drain.
You can try to draw on the screen as well. I think annotation is allowed for everybody. You can actually draw with the annotation tool.
Yes, that seems like I can. Well, okay, so what is like those two black parts?
Oh, the black part is, I think it's oxide, isn't it? I think the black part is just insulating oxide.
Okay, but then, okay. But then when
I don't know how they build that part of the multi-channel transistor. You can ask me, but I really know nothing. You'd have to go read about it.
Okay. Yeah. And then these two though are one of the source and the other drain, right?
Yeah.
Okay.
And then the yellow is the gate.
And the yellow was the gate.
Now, what's special about? Does this transistor have a kappa? What is kappa for this transistor? What would kappa be? Remember, kappa is coming from the backgate effect, right? It's the fact that the backgate is pulling on the surface potential, and the front gate is pulling it up, and the backgate is pulling it down. The bulk. Is there a bulk here? There's no bulk, right? Yeah, so kappa should be 1. It should be like perfectly ideal transistor. As ideal as you can make something that uses single electrons. So that's really nice. And FinFET almost has a kappa of 1. Actually, the FinFET almost has a kappa of 1, right? But there's a little bit of backgate effect through this this region down here at the bottom of the transistor. But most of kappa is almost 1 for a FinFET, but it's not perfectly controlled by the gate, right? Because there's a backside here that's not controlled by the gate. It's still pulling on the channel a little bit. Okay. So you can't get kappa bigger than 1. Doesn't exist, as far as I know. There's no magic material that gives you kappa bigger than 1. Okay, so that's all I want to say about transistor technology. Now the rest is all about memory technology. It's about new non-volatile memory technology past DRAM and SRAM. So you're probably familiar with this SRAM memory cell, which you can build in any CMOS technology. It's basically a cross-coupled inverter. You see you have 2 digital inverter. Here's one inverter, and its output of this inverter is connected to the input of the other inverter. And the output of this inverter, it should be a dot here, actually, is connected to the input of this inverter. So these 2 inverters are cross-coupled. So if one is high, if the output of one is high, then it's driving the input of the other high, which is driving the output of the other one low, which is driving the input of the first one low, which is making the output high, and vice versa. So it's stable in one configuration or the other, either 0, 1, or 1, 0. And when you want to override it, you turn on these transistors here and force the inverter output to be the new bit value. Like if it was 0, 1 before, you could force it to 1, 0 by just forcing it that way with a big, strong thing, and then it'll hold that state. So that's the SRAM memory cell. It's used all over the place for local buffer memory. In fact, the design rules for these SRAM macro cells, these macros, these memory compilers that build this circuit are heavily optimized to make this thing as dense as possible. And they really violate some of the standard design rules. So they really get a bit higher density. Problem is, it's quite area expensive. In fact, the area of this SRAM is about 20 times bigger in the same technology size as a dynamic random access memory cell, a DRAM cell, which is 1 transistor and 1 capacitor. When you want to save a bit on this DRAM cell, you just turn on the transistor and either put a 1 or a 0 on the capacitor. You turn off the transistor. When you want to read it, you turn on the transistor, dump the charge, sense whether it was a 1 or a 0, and then write it back before you turn off the transistor again. So these DRAM cells have to be refreshed over and over again, but they're much, much denser, like 20 times denser. So 20 times less expensive. And that's why, of course, you know, the main memory on every PC, every smartphone is DRAM. But DRAM, you know, has to be read in a very particular way. It's only efficient to read it when you, because of the way it's built, it's only efficient to read DRAM if you do it in a row by row way, so that you read in parallel a whole row of bit values. And SRAM, you can kind of individually address particular bits and read and write them at the same speed. But all these are volatile memory storage sources, places. But what we're speaking about here is more non-volatile memories like flash memory. In flash memory, the memory is stored as the amount of charge on a floating gate. Now, I want to tell you a little bit about the amazing scaling of flash memory technology, because it really is truly remarkable. Despite all the talk about memristors and different kinds of new non-volatile memories, flash is just remarkable. Maybe somebody here knows quite a bit more about flash. I don't know much about it myself. But the idea in flash memory is that you have a transistor. This transistor right here has a source and a drain. Then you have the addressing gate, which is for programming the transistor. It just turns on the transistor. And you also have a floating gate. The floating gate is sitting right here. The floating gate is not connected to anything. It just holds the charge that you put onto it, either by shooting it on by hot electrons. So you get electrons going really, really fast from the source to the drain. And they go so fast that they actually tunnel across the oxide and onto the floating gate. They don't tunnel across, they just shoot across because of their high energy. They can cross the energy barrier of the oxide and they can get onto the gate. Or you could tunnel the electrons off the floating gate through the thin oxide onto this control gate. So you can get the electrons on and off this floating gate. It costs, there's a question. It costs a lot of energy to do it and it's slow, but once you have the stuff there, it's stored basically forever. Somebody asked a question here. Oh yeah, so there's a question about the DRAM. That's actually a really great question, thank you. How large is the size of the capacitor in DRAM compared to the transistor? So this capacitor is not like the capacitors that you're used to, you know, drawing with metal layer flat capacitors. These capacitors you have in DRAM memory chips are actually circular or cylindrical capacitors that stick up out of the silicon, or they're going down into the silicon bulk. They're highly optimized to get the maximum capacitance in the smallest possible area. And we'll see in a moment how big the whole memory cell is. There's something called F squared, how big the memory cell is in F squared, feature size squared. But talking about flash memory, you basically are storing charge permanently onto this floating gate by either tunneling or hot electron injection. And so if you want to program this isn't a very good picture here, but basically you get this thing you put the drain, say, at 12 volts, the source is at 0 volts, and the gate is at 12 volts. So this is an NFET, it's on really hard. The electrons are shot from source to drain. Remember, the drain voltage is 12 volts here, right? So the electrons can pick up a lot of kinetic energy, so much that they can cross the 8 electron volt oxide energy barrier and get onto the floating gate. That's how you get them onto the oxide. When you want to get them off here, you open the source, you tie the drain to 12 volts, and you tie the gate now to 0 volts. And now you have a very high voltage across this floating gate between this control gate is at a lower voltage than the floating gate, right? So the electrons could actually tunnel across this very thin oxide here and get off the floating gate. Okay, that's the principle. Now we can look at this comparison of different memory technologies. In SRAM, which is static random access memory, dynamic random access memory, and so-called NAND flash. I'll explain what that is in a minute, as best I know it. So do these retain data? These are volatile, and this one's non-volatile. This is the cell factor in F squared. F squared is the square of the feature size. So whatever technology node you're at, you're going to have some number of F squared. It's the size of the cell. So an SRAM cell is between 50 and 120 F squared. A DRAM is between 6 and 10. So you can see it's well, actually, I think it's smaller than this. This says about 10 times smaller in area, but I think it's actually in reality more like 20 times factor smaller. And then a NAND flash cell that's even smaller than DRAM. And the other important thing is how quickly you can read the cell. See, SRAM is really fast, DRAM is slower, and how many times you can write it before it wears out. I mean, this is just CMOS technology, so you can basically read and write it forever. But if you're doing NAND flash or something, you're doing a kind of destructive high voltage operation, which can damage the oxide. So you can't read and write it that many times. And how much power it takes to read and write it is very low for CMOS, but much higher for flash. And whether it burns power statically, right? SRAM burns static leakage power because you have to keep the power on to keep the latch activated. And in DRAM, you have to constantly refresh the memory cell. In NAND flash, it doesn't burn any power when you turn it off, just charge stored on a floating gate. And so, like I said, F is the feature size here. This is really good. DRAM area is really small, but the advantage of NAND flash, even smaller memory cell size, but it's really slow to write it, especially. And the read and write power is quite high. I'm not sure why the read power is so high, but the write power for sure is high. Because you have to burn millions and millions of electrons to get one electron onto the floating gate, even billions. It's just not very efficient. Okay, so you guys may know more about this than I do, but you can imagine if you have flash memory cells, how can you actually make a memory out of it? So there's so-called NOR flash and NAND flash, and there's even other kinds called VNAND and stuff like that. But the basic difference between NOR flash and NAND flash is that the way the memory cells are, each one of these is a floating gate memory cell, how they're organized to store bits. And in a NOR flash, they're organized in a wired NOR circuit. So all the these blue lines here are the so-called word lines that select which address you want to read out. And the red lines are the bit lines where you read out the actual bits that are stored. And in NOR flash, you see the FETs are organized so that the bit lines connect the one side of the transistor to the word line connects from one side of the transistor to the bit line. And then the word line comes in and activates the gate. And it's called NOR because if any of these guys is on here, it can pull the bit line high. But this is a NOR configuration, right? Where these guys are wired in parallel to this bit line. Okay, so the word lines come in on the gates. Actually, the blue lines are called source lines. And the other side of the floating gate transistor is hooked up to the bit line. In a NAND flash configuration, the different bits that are stored in a cell are wired up in series to the bit line. And this is a much, much denser configuration because you don't have to have a separate contact to the point in between the transistors. You see, this is just a gate here crossing active regions. Now, what's not clear to me exactly is how you store individual bits in this NAND flash structure, because presumably you have like 8 of these cells in a row, right? So that's like 1 byte of storage. And if you want to store a byte in there, which consists of zeros and ones, presumably this is an access device down here, but here you have all the floating gates, right? So you have an access device here, and then you have a bunch of these floating gate flash cells. So if you want to store a particular byte in here, some of these floating gates are going to be high and others are going to be low. And how you determine what word is stored there is not so clear to me when it's set up in this NAND configuration, right? Because it seems to me like if you want to see if some memory is stored in here, you have to set the word lines to the right configuration, either high or low, to check whether current flows through here. You understand? It's a little bit confusing to me how you store a bit in here. Does anybody know the answer to this? Okay. I'm not actually sure. Do you know, Rudy? Yeah?
No, I don't know, but I also wanted to ask you one thing. Like,
You agree that you can store a bit on each one of these gates, either a high or low bit on each one of these gates, but how you know whether that bit is stored there or not when they're wired up in a series configuration is not so clear to me, because the only thing you can check is whether current flows through this whole string or not by putting bits onto these blue gate lines. Now you can check how much current flows, but basically either current flows or it doesn't. It current flows if all these guys are on, right?
Yes.
Yeah.
But
So
also in the NOR, like we want to check we want to like get the bits in the word line, I guess. In the NOR,
so let's assume one byte is stored in each cell, right? So this is actually eight transistors in series. So you have a byte stored in here, which is programmed by either charge is on the floating gate or it's not on the floating gate. So now you've got to check what series of bits is stored here. And you can put the word lines high or low. And then you can also turn on these transistors at top or bottom. So it's not entirely clear to me. I mean, you can imagine information is stored in those bits, but we'll have to leave it for next time to see how you actually get at that information. But you can see because of this arrangement, the reading out the NAND configuration of the flash is going to be much more complicated than reading the NOR configuration. In the NOR configuration, if you want to see if the bit cell is storing a bit or not, you just raise the word line high. And if there's a bit stored there, then there'll be a connection between the bit line and the blue source line. So current will flow, and you can just see whether individual bits have information or not. I mean, if the floating gate has a low voltage in it, then less current will flow than if it has a high voltage, right? You can easily read individual bits. Anyway, that's the organization of this NAND flash memory. Here, there's a table here that you can look at yourself about the advantage and disadvantage of the NOR configuration. But basically, I'll just tell you that the kind of stuff, flash memory that you have in your smartphone, your USB stick, is all NAND flash. I'm not sure that NOR flash is used that much anymore, although you can buy discrete chips with NOR flash if you want more speed or easier interfacing, but they're much lower density. Okay, now here's the cool thing. This is what it actually looks like. And I encourage you to look at this 3D NAND flash wars begins from 2018. So you see here in this picture, you have the floating gate memory cells are actually at the crossing points of these word lines and these bit lines. And it's really a 3D structure here. Here you have the blue metal bit lines. They are the bit line contacts. They're connected to the source gate. I think it's, I don't know what SGD stands for, but this is SG drain and SG source. And then there's a source plate to power that. But the flash memory cell is actually at the crossing points of this crossbar, which is super dense here. And so that's the structure of this NAND flash cell, which has a whole bunch of these in parallel. Each one has like 8 of these, and there's hundreds and hundreds of them in parallel like this. But that's not where it ends. So people said, we need more density for this flash memory. So what can we do besides this? So then people came up with 3D VNAND technology. It's even cooler. So instead of using floating gate technology, they used what's called charge trapping flash. And the charge is stored on a silicon nitride film. And this is commercialized in 2002, long time ago. So if you look at this, don't know how this charge trapping layer works. I hardly know anything about that, to be honest, but basically you have a tunnel oxide and then you have a so-called charge trapping layer, which I think is not oxide, and then you have a control gate. But this is the principle of the thing where you can store charge or not in these 3 things. But if you actually look at it, the structure is red is polysilicon, yellow is silicon nitride where the charge is trapped. It's silicon nitride, not silicon oxide. And blue in between is silicon dioxide insulator. Now, this VNAND technology actually looks like this, so it's even more complicated. So here's a 3D NAND architecture where you have multiple layers stacked up. So this is not looking like a silicon chip at all. I mean, it's really looking like a 3D honeycomb mesh structure. In fact, in 2020, they were already shooting for 256 layer thick VNAND technology. And this is how they fit. I mean, it's just incredible. This is how they fit 128 gigabytes into this tiny little SIM card that you stick in your smartphone. You think about it, you have a card that's literally like half a centimeter on the side and about at most 1 millimeter thick, and they're cramming 128 gigabytes, you know, a terabit of memory using this stuff. I mean, it's really amazing. But this is, again, by this charge trapping technology. I won't try to explain how it all works. I don't really understand it, but it's really an incredibly complex 3D structure, which is very complex error correcting circuits and stuff to read it out. Okay, this is a superficial view of it. Okay, but now I'm going to show you a little bit about the latest memory technology, which is so-called memristor memory technology. So again, there's a comparison between different memory technologies, SRAM, DRAM, NAND flash, and now you have these other memories called phase change memory, spin torque transfer, random access memory, and resistive random access memory. And here's a kind of a slightly speculative comparison table comparing these different memory. But first, let me tell you. So here's the definitions of SRAM, spin torque transfer RAM, phase change memory, and resistive random access memory. So let's take a look at those. So these resistive memory devices, by contrast with floating gate technologies like flash, where you store the charge on a floating gate and it's surrounded by an insulator, in resistive memory devices, you somehow change the physical structure of material between two electrodes. And as I understand it, there are two broad families of that. One is a metal oxide family, where what you do when you change the structure is you form these filamentary conductors between the two sides. These are like narrow little hairs, conductive hairs that can connect the two sides like lightning bolts from one side to the other. And depending on the number of those little tendrils that connect from one side to the other, the conductance changes. That's one family. And that's the metal oxide devices. And then you also have the other family, which is so-called phase change devices, where you change the phase of the material from a crystalline to an amorphous type. And that always starts on one end, where you have the kind of like thing and then a mushroom growing out from it. And so what you're doing is actually physically changing the structure of this material, which is either metal oxide or some, I don't remember what, there's a whole bunch of different materials that people try. And by the way, at IBM Merschlikon, they're big experts on this phase change, this type over here, not the metal oxide so much, but this kind where you get a donut. And you basically change the material by passing current through it and heating it up. So if you heat it up, heat it up and then cool it down slowly, you can get rid of this mushroom. So you can turn it into more crystalline material. If you heat it up and then let it cool really quickly, then you get this amorphous material, and it has, I think, higher resistance in that state. I'm not sure which way it is. So those are the two broad families of these resistive memory devices. Now that's different than the phase change, the spin torque transfer. A spin torque transfer MRAM, or magnetic RAM, actually changes the magnetic polarization of a layer between two other layers. And depending on the polarization of that magnetic material, the current through the transistor that lies underneath is modulated a little bit up or down. In that case, you change the magnetism of the material. Okay. So that's a magnetoresistive random access memory, or MRAM. And you can see the picture right here. You have a transistor. It has a source line and it has a drain line. Yeah, so actually the MRAM material is actually on the drain. It's in series with the drain. So this blue stuff here has a ferromagnetic layer surrounding a tunneling insulating layer. And somehow by the voltage or the current you apply here, you can slightly change the magnetism of that, and that modulates the drain current. And so you get like a few percent change in the drain current, depending on whether the cell stores a 1 or a 0. Yeah, and here this RRAM, which is the metal oxide type that I showed you on the previous one. So the RRAM has the titanium dioxide or some variant of it surrounded by platinum wires. You can get these tendrils between the two sides, and the phase change material, you get this like donut-like cap of polycrystalline material. Okay, so these are broadly classified as memristive devices. They're resistive devices that kind of have a memory. And they were predicted as the 4th class of device by Leon Chua in his famous Berkeley paper. And ever since that paper, I think it was about 30 years ago, people have been trying to turn this stuff into mass production technology. There was a question from Federico about, I don't know when this replied to, I just noticed it. Could the gates be sweeped? Only one gate off per line if floating gate set? Oh, this is about the NAND. Yeah, I'm not sure about that. Let's leave that for now. I just want to finish talking about this memristor device. There's a very famous picture, I think it was on the cover of IEEE Spectrum, of memristor wires from HP Labs. So these are actually, every place the wires cross this other wire, you had this memristive material in between. I'm not sure what it was. I think it was one of these metal oxide devices. So RRAM type. But the idea is that every time you get a crossing like this, you can store a bit. And so it offers a potential of extremely dense storage of non-volatile information, right? If you could somehow store a bit in the resistive connection between these two wires. Now, there's all kinds of practical problems, huge number of practical problems. And one of them is that you actually need an access device or a selector device to isolate individual crossing points. You need to make that point a bit clear here by drawing an illustration. Let's suppose that you had maybe it's actually shown here, yeah. Suppose you had such a crossbar memory array, right, where you had a bunch of wires going in the X direction and a bunch more wires not connected to them except by these memristor devices in the Y direction. So in principle, what you can do with these is store weights of some vector matrix multiplication on these resistors, right? And so then if you want to multiply this vector X times a matrix A, you just store the weights of the matrix in the conductance values. So now you apply the voltages X, they get multiplied by the conductances A, you hold the Y's at some particular voltage, like say 0 volts, and then you read out the current, right? So the output current Y1 is just the weighted sum of the conductance times the voltage X1, plus this conductance times X2. And so in one step, you could do this vector matrix multiplication. That's the basic idea, right, of this kind of vector matrix multiplication. The problem is, how do you actually store that resistance value? So if you want to access this particular resistor here to pass a current through it, to change its resistance value, because that's how you change one of these devices. How do you access it? Well, you have to control Y and X and pass a current through here, but you don't want current to pass through any of the other resistors because that'll modify them. So you've got to somehow individually access this conductance, but not access any of the others. And so it gets super slow to do that. If you have to do it one by one, right? You could just you could open Y2 through YM and X2 through XM, so no current can flow through them. Now you raise X1 to a high voltage and Y1, and you put Y1 at a low voltage. Okay, but still it's hard to see how the current will not pass through the other devices. So you need some nonlinear thing that can prevent the current flowing through the device, through the devices in one direction, only let it through in one direction. And so you always need this nonlinear element or selector device to isolate individual crossings. And people do now have solutions for these so-called nonlinear, like diode-like selector devices. For example, in Intel's 3D crosspoint technology, they have these vertical selector devices, these vertical diodes that can kind of isolate these individual memristors. But it's a specialized technology, like everything. But it's not something you get in a normal process. You need an extra technology to do that. And those have mismatched themselves. So that's one of the big problems. It's not just having the memristor, but also the selector device. Okay. Anyway, people got very excited about these memristor devices because of the possibility of doing things like spike time dependent plasticity rules using a phase change memory crossbar. And the main idea of a spike time dependent plasticity is the idea of causality in spiking neurons. So if this postsynaptic neuron here emits a spike and that spike was caused by a nerve impulse coming in on one of its synapses just shortly before, then there's kind of a causal rule that says, oh yeah, that input spike actually caused the output spike. And so you can observe in the nervous system that some synapses at least obey the spike timing dependent plasticity rule, that if the neuron fires because a spike came in on a synapse, then that synapse is strengthened. If it doesn't fire, if a synapse comes in, if an incoming spike comes to a synapse and the neuron doesn't fire, then the synapse is weakened. And so you can imagine doing the same things with these crossbar arrays. You know, your input spikes would come in here on the blue wires, and if they cause an output spike on the other crossing wires, then maybe you should make the synaptic strength stronger, something like that. It's a bit unclear exactly how to do that. And people notice that when they take these phase change memory cells, you can tell they're these things because they have these little donuts on them. See, they're depressed, they're amorphous, right? It means they're weak. You can see that as a function of the pulse number, the resistance actually increases, right? If you give more and more pulses and you make it more and more amorphous, like you heat it up and quench it really quickly, it becomes amorphous instead of crystalline. Then as a function of these individual pulses, these red pulses here, I guess shown on this presynaptic thing, you can make the resistance go up. And then if you give smaller pulses, like the blue ones here, you can make the resistance go back down again. Now, I'm not sure why the smaller pulses make the resistance go back down again. I guess it just heats it up a little bit and cools it, and that brings it more into an ordered state. So then people have managed to show, in at least academically in some papers, they were able to implement some kind of a spike timing dependent plasticity rule, where this is the relative spike timing in milliseconds between the presynaptic neuron and the postsynaptic neuron, and this is the synaptic weight change in percent. So if the presynaptic spike comes, like say, 20 milliseconds before the postsynaptic one, then you want to strengthen the synapse. And in fact, they managed to show that they could strengthen the synapse by like 50% then, right? So the pre came before the post. But if the presynaptic spike comes after the postsynaptic neuron fires, then you should weaken the synapse. And they managed to show that some of these memristive materials were able to demonstrate these kind of STDP rules that mimic what you see in neuroscience. So open circles are what you see for real. At least one famous neuron in this bee and poo paper from USC, 30 years ago, they managed to show that some synapses obey these kind of rules. Only it's complicated. Nobody's actually demonstrated that you can build a useful thing out of this, right? It's just an idea so far. But anyway, people were intrigued by the idea of spike timing and whether timing could be used to change the weights instead of doing this, this gradient descent back propagation. Could you actually learn with local learning rules? So people are still excited about that, and they're still working on it, although not with much to show for it so far in terms of practical application. And the biggest problems are that the device variability is huge. Like if you build a big array of these phase change memory synapses, you might get a factor of 1,000 difference between the fastest ones and the slowest ones in terms of how fast they change their weight. And they're strongly temperature dependent, and there's all kinds of history dependence. It's really complicated. And so if you just make a pre and post synaptic correlation like that, the weight change might be 1% and it might be 50%. You can't predict it. It depends very much on the individual device. So it's difficult. But like people like Abu Sebastian down at IBM Merschlicon, they've showed these convincing demonstrations that you can use these vector matrix. You can use these arrays of these devices in this crossbar arrangement to do linear algebra, for example. They can do big vector matrix multiplications in a single clock cycle. But do you know what the problem with that is? There's two big problems. So first of all, you need to have a, you have device. So when you want to store a value on one of the resistive devices, you have to do it in a feedback loop. In other words, you have to program each one individually in a feedback loop because the variability of the open loop programming is just too big. So you have to like program it, check it, program it, check it. So it takes many cycles. So it's very slow to program the matrix. And because of non-idealities and non-linearities in these connectance values, you always have to use a pair of these values for the plus and minus halves of your value. So you have to do like a differential operation. And it's actually quite power hungry because instead of putting a digital input and having a digital output, you need an analog input and you need to read an analog output. So you need data A converters here, convert digital to analog, and you need A to D converters here to convert the analog outputs to digital again. So you need these big, kind of rather fast and power hungry converters on each side of the thing. And the biggest problem nowadays in connection with deep learning is that there's no way to share the weights. Like in a CNN, you have this kernel that's used over and over again for different parts of the image. But here, every weight is just used once per operation. So there's no way to have shared weight operations. You can't really share that weight to use it over and over again. And not in an obvious way like you do for CNNs, where you can just easily replicate the weight or pass it over the image. Okay, that was a bit of a core dump, but anyway, that's what I wanted to tell you about future device technologies and memory technologies. And maybe you have some questions you can raise in the discussion. I encourage you to go read the popular articles about this because usually they're quite well written and they explain it for beginners. Okay?
Yeah, that's cool.
That's good? Okay. All right, it's been fun. We'll see you next week. And next week, we do plan to have a little bit about this mystery, and then we'll maybe go over the study sheet for the course, for the exam. And then we'll try to put together some live demos and stuff as much as possible that we can do remotely.